And I suggest that we go for the next presentation by Campo Nogara and colleagues. So the presentation will be about relationship between Amazon biomass burning, aerosols, and rainfall over the Plata Basin.
Okay, well, I will start with a climatological distribution of mesoscale convective systems over South America. And we can see here that over La Plata Basin in the summer and the spring, we have a lot of systems over this region. So here's about biomass burning figure, and the red pixels are fire locations, and we can see here that the August dry season, we have intense biomass burning over Amazon, Central Brazil, Paraguay, and Bolivia. So this is a schematic figure, and the first graphic in the top is about AOD for Hillbank stationed aeronet. So we can see high values of AOD in the dry season. And the same pattern is possible to see in Alta Floresta. But in the Alta Floresta, the values are higher than Rio Branco. And here is a climatological rainfall that I get from the tree data. So we can see high values of rainfall over Asunción, Santa Maria, and Buenos Aires that is located over La Plata Basin. And according to Freitas et al. 2005, aerosol from biomass burning in Amazon and central Brazil are advected via low-level jet here to La Plata Basin in the dry season. So the objective of my work is to investigate this relationship between the aerosols and the rainfall over La Plata Basin. I filtered the data, keeping cases with north wind over the blue rectangle, this region where I showed you that there are several systems here in the dry season. So I keep cases with minimum rainfall over the red rectangle. That is the path of aerosol. So I want to avoid cleaning up the air mass during the path. Here's the biomass burning region. So I calculated the average rainfall rates over the blue rectangle. So to do this, I calculate daily rainfall for each grid point inside this rectangle, and I sum these points and divided by the number of points, and times 2, divided by number of points. Yes, okay. I'm nervous. So here's the first result. It's a beam plot, okay? To do this, I get the beam width of aerosol equal 0.1 and AOD, sorry, and is this axis. Beside this beam, I did the mean already rainfall rate. So as for our station, we can see here that when AOD increase the same time, aerosol average rainfall AOD increase, average rainfall decrease for all stations. Here's a kind of beam plot too. So this axis is rainfall fraction, and here is AOD. So to rain fraction in this case is percent of rainy grid points. To calculate this, I got the number of rainy grid points and divided by all grid points and times to same percent, 100%. Sorry. And we don't have contracts between the beams, so I don't detect aerosol effect here. However, above 40%, there are more contracts, so there are aerosol effect. So here is the same idea, but for omega. In this case, this omega is average over blue rectangle at 500 hectopascals. And the beam width for omega was 1. And for aerosol was 0.5. So we can see here that for low values of omega, we have a tendency to decrease precipitation with increase of AOD for all stations. And we have high values of omega, we can see this pattern. The second column is average rainfall rate for n times. Third column is omega. And the fourth column is relative humidity. The relative humidity is mean relative humidity between 7 and 500 hectopascals averaged over blue rectangle. So here we have a variance explained for combined UF for first and second eigenvalues for each station. We can see here that the first UF has 40% of variance explained. It's high value. And the second UF has 30%. Together, this UF have 70% of the variance explained of the data. So here is a combined UF, the UF 1 and 2. The first line is UF 1 and the second line is UF 2. So for each mode, each component, AUD, rainfall, humidity. So in this case, the second UF detected aerosol effect that suppress the rain because the signals are different here. Sorry. So high values of AOD suppress the rain for all stations here. So the conclusions are, for beam analysis, aerosol effect is detected by rainfall fraction above 40%. For weak omega, large AOD loads tend to suppress rainfall. Combined, now for combined UF, the first UF explains 40% of variance. This UF detected the dynamic forcing. And the second UF explains 30% of variance and detected aerosol forcing that, in this case, suppress the convection, or the rainfall, sorry. So, the next steps, I will use the numeric modeling to understand the effect of advective aerosol on the rainfall of mesoscale convective systems over La Plata Basin. These effects are radiative and microphysical. Okay, thank you.
Thank you very much. We have time for a couple of questions. Please.
High population, like lightning, only the rainfall that we have very good drops,
So I didn't look for deep convection. I get only the precipitation values, but high precipitation value, because rain fractions above 40%, you have high precipitation values, and probably a deep convection. But I didn't look for deep convection only. Yes, 12 years.
Argue that their seasonal cycles are not simply correlations between dry years where there is going to be more biomass origin and less precipitation, but there is less moisture. That wet years where you have less biomass origin in the Amazon than the forest, but you have more moisture for the forest. How do you compare these two?
Because I was looking to dynamic patterns. Omega, with omega we can separate the high values and the low values, and I didn't look with more pay attention for this question, but I think that the next steps I will look with more attention. So because it's a preliminary study of the aerosol effect. Yeah. To try to understand, you have separated the patterns, dynamic patterns, from aerosol patterns.
You just said that more than 40% means that you have a strong convection. That's not true, because we're looking for fractions. So the intensity is really depending how you calculate the fraction. It means that convection is not isolated. It's a spread that does not mean intensity. But I would just comment that weather results using land data and radar data shows that something that is still open in your results, that during the precipitation increase when you have more increased AOD, for the case, only for the case when you have strong cape. So when you're doing strong cape conditions, if you increase the number of black carbon, you increase precipitation. In the other case, you always have to decrease the precipitation. So it's a result that fit inside the result because you didn't find. But when you use vertical motion, then it goes to cape. So you didn't find it.
No, I didn't find. I tried to use cape with your songs, but the period of data decreased a lot. So I prefer to use omega.